Welcome to G Fun Facts Online, where we explore the biggest wonders of our universe. Today, we're going dark. Not in a scary way, but in a most of the universe is completely invisible kind of way. What if I told you that everything we can see, every star, every galaxy, every planet, makes up only about 15% of the total matter out there? The other 85% is a mysterious, invisible substance called dark matter. It doesn't emit light, it doesn't reflect light, it doesn't interact with us at all, yet it forms the vast, unseen cosmic web that dictates the entire structure of our universe. So how do you map something you can't see? Well, it turns out we have a cosmic cheat code, a trick of light and gravity that Albert Einstein predicted over a century ago. And now, we're supercharging that trick with one of the most powerful tools of the 21st century, artificial intelligence. Get ready, because we're about to learn how to see the invisible. Einstein's theory of general relativity tells us that massive objects bend the very fabric of space-time around them. Think of it like placing a bowling ball on a trampoline. This curvature doesn't just affect objects, it also affects light. When light from a very distant galaxy travels towards us, and it passes by a massive galaxy or cluster of galaxies in the foreground, its path gets bent. This foreground object acts like a giant, natural magnifying glass. This effect is called gravitational lensing, and it's our key to unlocking the dark universe. Sometimes, if the alignment is just right, this lensing effect is incredibly dramatic. It can stretch the light from the background galaxy into mesmerizing arcs, or even create multiple images of the same galaxy scattered around the foreground lens. In the most perfect, rare alignment, it can smear the light into a complete circle, a stunning cosmic halo known as an Einstein ring. This is called strong lensing, but most of the time, the effect is much more subtle. This is weak lensing, where the shapes of background galaxies are only slightly distorted. The distortion is so tiny that you can only detect it by looking at the average shapes of thousands upon thousands of galaxies in one patch of sky. By measuring these distortions, both strong and weak, astronomers can work backward. They can calculate the total mass of the foreground object that's bending the light. And since they know how much mass the visible stars and gas should have, anything left over must be the mass of the invisible dark matter halo surrounding it. Gravitational lensing is the only tool we have that can directly measure and map the distribution of dark matter. For decades, finding these lenses was like searching for a needle in a cosmic haystack. Astronomers had to manually scan millions of images, a painstaking and slow process, but today, we're facing a data tsunami. Telescopes are capturing billions of images. The upcoming Vera C. Rubin Observatory in Chile is expected to generate a staggering 500 petabytes of data. As Lawrence Perot-Levasseur, a fellow at the SLAC National Accelerator Laboratory, puts it, we won't have enough people to analyze all these data in a timely manner with the traditional methods. The era of the human-only search is over. Enter the AI astronomer. Scientists are now training a type of artificial intelligence called a convolutional neural network, or CNN, to do the searching for them. These networks are inspired by the human brain's visual cortex and are amazing at spotting patterns in images. Researchers feed the AI hundreds of thousands of computer-simulated images. Some contain fake gravitational lenses and some don't. The AI churns through them, learning to recognize the telltale signs, the unique arcs and rings of light that signal a cosmic lens. Once trained, these AI models can sift through millions of real astronomical images in seconds, finding potential lenses with incredible accuracy. A task that would take a team of experts weeks or months is now done in the blink of an eye. And the results are already pouring in. The European Space Agency's Euclid Space Telescope, launched in 2023, is on a mission to map the dark universe. In its very first major data release, AI algorithms have already helped identify around 500 new strong gravitational lens candidates. That nearly doubles the number we previously knew about from space telescopes. One of its most stunning early finds is a beautiful new Einstein ring, nicknamed Altair's ring, formed by a galaxy 4.5 billion light-years away. Discoveries like this are gold mines for cosmologists. But here's a fascinating twist. This AI revolution hasn't made humans obsolete. In fact, it's created a powerful partnership. While AI is incredibly fast, it can sometimes be fooled by things that look like lenses but aren't, like spiral galaxies or glitches in the image. This is where you come in. Citizen science projects like space warps invite members of the public to look at the candidates flagged by the AI. The human eye is still one of the best pattern recognition tools on the planet, and volunteers help to verify the AI's findings, separating the real cosmic lenses from the false alarms. As PhD student Natalie Lines from the University of Portsmouth said, currently the best tool for detecting gravitational lenses is the human brain, but we cannot get humans to inspect over 1 million objects. So AI does the heavy lifting, and an army of citizen scientists provides the crucial final check. We are truly entering a golden age of cosmology. When the Vera C. Rubin Observatory comes fully online, its car-sized, 3,200 megapixel camera will survey the entire southern sky every few nights for 10 years. It's specifically designed to map dark matter by measuring the weak lensing of billions of galaxies. The sheer volume of this data makes AI not just helpful, but absolutely essential. These new, AI-powered maps of the dark universe will help us tackle the biggest questions in physics. What is dark matter made of? What is the mysterious dark energy that's causing the expansion of the universe to accelerate? Will we need to revise Einstein's theory of gravity to explain what we see? By teaching machines to see the subtle ways gravity paints the cosmos, we are charting the unseen. We are finally bringing the hidden architecture of our universe into focus.